Okay, I've started the recording. I'm audible, right? Well,
Yes, audible.
okay, good. Okay, good evening to week 5 tutorial of computational complexity. Okay, and again, my name is Papyadeep Rai, and these tutorials will happen every Tuesday, 6 p.m. to 8 p.m. Okay. Right. So let's get straight into business. So today's topic is this week's topic is BGS Baker Gill Solovay theorem and randomized randomized complexity classes. Okay. So before I enter this week's topic, like always, I will pick some questions from the previous week's assignment, which is week 4. Since this deadline is already over, I'll be discussing the questions from there which were on the tougher side. So I think the previous week's question, there were only a handful of questions which are a bit challenging, according to my personal view. So let's see that first. Okay. So here is one question. Okay, here is one question. So this page, let me shift it earlier. Okay, yeah, good. So this is question 10. So we'll discuss this first, okay, before we enter this week's content. Consider the problem of 3 colorability, that is deciding if a given underwriter graph is 3 colorable or not. Okay, if the graph is given as an adjacency list, which of the following is the smallest class that contains 3 colorability? Okay, so different possibilities. Yeah, go ahead.
Yes, so C colorability as such is NP-complete.
Okay.
But then all the complexity classes here belongs to the space complexity class, and the graph is represented as an adjacency list.
Right.
So whether the graph is 3 colorable or not, and from the space viewpoint. So yeah, I need to check three things at a time.
Right.
That and to check 3 things at a time, probably the I need to just, but not only this thing, but I'll have to check that okay the adjacency. So vertex number 1 is connected to adjacency list. So I have to maintain the colors, and then there are the number of the vertices. So yeah, I'm a little doubtful, but probably V space V and then log V would be sufficient to check this thing, because
Okay.
I'll have to check this thing for the number of the vertices, and for every vertex I need to keep the track of the pointers, and for that I would be requiring log the amount of the space.
Right. Okay. Okay. Yeah. Yeah, that's good. And so you think, yeah, but that is a good bet actually, because this log V that you are seeing is probably because of because some encoding, right? Because you are using some kind of numbering scheme, right? And to refer to a particular vertex, right? That's what you mean.
Yes.
Yeah. Okay. But the interesting thing is actually we can get rid of that. But can you think of a okay? Suraj is here. Hi, Suraj. Welcome to week 5. Um, anyway, think of the most naive algorithm. Okay, need not be very fancy. Think of the most naive algorithm that will capture 3 color, that can solve 3 color. Can you give an example? what is the most simple and what is very brute force like?
So I'll have to check that no two adjacent vertices are having the same color.
Right.
So
But
I'll have to
yeah,
check the of the adjacent vertices.
right,
I will go back to the entire set of the vertices, and
right.
then I will check the colors of the adjacent vertices, whether the color is same or not same.
But who's giving you these colors?
Okay, right. So I would be assigning colors,
Right.
but then I would be assigning colors.
Exactly.
Okay, so
Yeah.
the point here is that yes, so I will assign one color to a vertex. I will assign the second color to the second vertex. I will try to assign the third color to the third vertex, and then
Right.
I'll try to see if I can reuse the first color or not.
Yeah, exactly. And that the algorithm that you are telling about reuse the other color or not, that is an even more clever algorithm. Okay, if you want to build a more naive algorithm, okay, that doesn't even have that kind of a cleverness, just assign the random colors and then go one by one and check whether it's violated, right?
Yes.
Yeah, good. Yeah, that is exactly the algorithm, the most naive algorithm. That's right. Now, so here it's written that the graph is given as an adjacency list. Okay, to confuse us. Actually, it does not matter here that whether it's given as an adjacency list or not, because adjacency list only handicaps us in terms of time. Okay, not in terms of space. Okay, so we are
Well,
talking about space classes here. Yeah.
why so?
Well, because see, an adjacency list, okay, is a linked list, right? It's kind of like a linked list. So, and if A is adjacent to B and it's adjacent to C and D and so on, then to check whether A is adjacent to D, I need to go across all of this, and then finally, and I encounter a D, and then I realize that okay, and in the worst case, what might happen is there are n locations. There are A is connected to n all the vertices. Okay, n minus one many vertices, and then the whatever I'm querying is at the end. The whether A is connected to a vertex V is at the end of the list. So that is the worst case, right? So in that case, how much time will I take? I'll take linear time to access.
Yes.
However, if I was given an adjacency matrix, right, then I just look at the corresponding entry of A and N, A and vertex V, and if your model is not something like a Turing machine, but in fact it's like a RAM machine, which directly can access the particular entries in the adjacency matrix, then how much time will it take? It will take constant time to get this particular entry. Is A connected to V or not? Can you?
Yes.
Right. So, but as far as space is concerned, we are not handicapped. Okay, because here also you'll need because here too something is my pencil out of charge. It is not. So how much space do I require? Well, to index into A and V, I need log n space, and again to perform this counting across the linked list, I need log n space. So as far as space is concerned, I'll need log n space anyway in both of them. So it does not handicap me whether I use a linked list or not, whether I use an adjacency list or not. Clear? So we'll come back now. Okay, we got it now. We don't be confused with adjacency list, adjacency matrix, and so on. It's only there to confuse us. All we care about is finding a very naive algorithm for three colorability. Getting it? So what do we do here? So what is three colorable? Okay, three colorable is all those graphs so that G can be properly colored with three colors, which means that no two adjacent, no two adjacent vertices can be colored the same color. So something like this is allowed, something like this is not allowed. Right. So that is about three colorability. So all graphs cannot be done this way. We can give counter examples for it. But what we are asking is, given a graph can be three colored. So the most naive way is take the graph and color all possible assignments on three colors. Getting it? So I do this. So you have a graph given to us, and then first I'll color this red, I'll color this blue, and color this red again, and blue, and red, and another. I take the same graph, and I do all possible combinations: red, blue, red. Okay, this time I use a different color. Let's see. Okay, let's say I use a green also. Let's say I use a green here. So I use a green here, I use a blue here, and I use a red here. Then every time, okay, and after each color assignment, check if proper coloring is violated. That is, what does it mean? That after I color I put one color on one vertex, another color on another vertex. What I do is I check if for all edge UV, okay. So this, okay, UV color of U is not equal to color of V. I check this across everything, and then that's it. If yes, then output yes, otherwise no. So now this is the simple algorithm. We go across all assignments of colorings and check whether coloring is ever violated. Okay. Now what is the space complexity of this algorithm? I have my work tape. Okay, I have the input tape. Okay. Input tape contains graph G. Okay. Now what does the work tape contain? What I'll do is, in the work tape, I'll put n cells. Okay. Size of V many cells. Okay. Size of V many cells. Now this particular cell, okay, this stands for vertex V1, this stands for vertex V2, this stands for V3, and so on, till if there are n many vertices in the graph, then what will I do? I'll have n many cells. Now I write here R for V1 is assigned red, B if V2 is assigned blue, and R again if V3 is assigned red, and green here if V4 is assigned blue, and so on. And then I do all possible combinations of this. How many possible combinations are there?
So for each cell, we have three possibilities.
Exactly. Right. First cell has three possibilities, second cell has three possibilities, and so on and so forth. So there are 3 to the size of v many possibilities. But remember, that is regarding time. What we can do is we can reuse space. So I do one possibility. Okay. I do one possibility, that is all r's. Second possibility is r and so on till rb. And third possibility r, rg, and keep doing this on the same space, reuse space. Then how much space am I using? I'm really using some constant which is actually just 2 bits extra to represent. Even if you are doing it binary, okay, I can represent red with 0 0, blue with 0 1, and green with 1 0, right? So the overhead is only 3, right? Sorry, 2 bits. So I can use 2 bits to represent red here, 2 bits to represent blue, 2 bits to represent green all over. So, and reuse space, and how much total space is equal to 2. So here you have 2 bits times the number of vertices, size of v, which is linear in the size of the graph. So d space n. Okay.
Yes.
Right. Well, the question is slightly flawed in a sense that it does not say. Suraj, is it clear by the way?
Yes, sir. TV.
Okay. Okay. So the question is slightly flawed in a sense that it says what is the exact containment. That we cannot tell. We cannot tell whether it is contained in root n, for example, because it may be so that somehow 3 colorability is contained in the space root n. Yeah. Hello. Oh, sorry. One moment.
Your video got freezed for some time and you were not audible.
Oh, okay. Yeah, sorry. I'll share it once again. Oh, okay. Oh, now is it fine now?
Yes. Now it's okay. So I could not understand that. So can you explain that thing again? That why do we require the space of the order of n?
Why do we require space of n?
Yes.
Okay. So you're fine with the algorithm, what the algorithm does?
Yes.
Okay. So now see, how many cells am I using here? Size of v many,
Yes.
the number of vertices, and the number of vertices is less than the representation of the graph.
Yes.
Because the graph is represented as an adjacency list, it takes what, almost n square, right? Order n square space. The size of vertex square. So size of g is at most size of v square. So g is not at most, equals order v square. So g is already greater than v, size of v, number of vertices, okay, which is the input itself. So I need v cells, right? What I'm saying is, each of these cells, okay, I'm using R to represent red, G to represent blue, and B to represent blue, and G to represent green. Suppose you tell me that is not fair. Suppose you tell me that you need to write it in binary, okay?
Yes.
If you need to write on the tape in binary, then what I can do is, to represent red, I can write 0 0. To represent blue, I can write 0 1, and green I can write 1 0 on the work tape. So there are size of v many cells. Each cell, so with 2 bits I can represent one color. So for each color, 2 bits times size of v, which is 2v, 2 size of v, which is less than the input size, right? The input size is some v square. So, and input size is nothing but n. So d space n. It takes
what this n here is.
So n is the input size. Always when we say, oh, okay. Sorry, the question is given in terms of v. Okay, not in terms of the actual input size. So which is Yeah, sorry for the confusion, which is 2v, which is order v. So d
Yes.
space order v. D space v. Order is already understood.
But then I have a question here that instead of I think that only three colors are sufficient to check. So therefore, I just require 2 into multiplied by the log of v number of the bits. So therefore, the space requirement now should be the d space log v.
What? Say it again.
Yes. So I would be requiring, I just need to check the colors of the 3 vertices only, that whether, at the most 4 vertices, that whether the color of all those vertices is same or not. So I would be requiring the space of the order of log v here. So on this tape, instead of storing the colors of all the v vertices, I just need to maintain the colors of the 3 vertices only, or at the most 4 vertices. Say whether the color of those vertices is same or not. So on the working tape, to measure the space complexity, I just need to maintain a pointer, and that I just need to store the colors of the 3 vertices.
No. That is not enough, because see, let's say you took any 3 vertices and then checked whether I can color this red, blue, and green, and I can always do that, because even if there is a cycle between this, it is always possible, right? Because even if this, if I take any 3, what you mean is go across all 3 size subsets, right?
Not all through all subsets. Why so? Because we are storing the vertices in an order.
Yeah, okay, that is fine. So I understand why it takes log space, but what you are saying is it takes 3 log v space. That's what you are saying, no?
Yes.
But okay, so I take 3 vertices, okay, and then
Yeah.
color them red, green, blue. Then
So
I
the
check.
colors have already been assigned on the input tape. The colors of all the vertices have already been assigned. But then the space.
But how can that be? Colors are already. This is a different problem. You're not talking about 3 coloring. In 3 coloring, you need to assign. You need to check if there is a coloring. Coloring is not given in the input.
But then I will. Okay.
Because what here we were doing is we are finding those colors by manually going across all possibilities. Okay.
Yes.
So I'll give you another argument why that does not work. Okay. Because you are saying it takes order, log, and space to solve 3 colorability. But if 3 colorability is order, log, and space, it means 3 colorability is in L. But L is in P. So 3 colorability would be in P.
Oh, yes.
Right. So this is another argument why this cannot be done in linear space. Not linear, log space. Okay. Okay, good. Okay, so but until here it's fine, right? You understood why D space V. Yeah, okay, good. So yeah, this is, I think you've seen padding already, right? How padding can be used. So what does padding do is it inflates the input so much that when you try to solve with a machine, you actually reduce the complexity of the input. So here is another question. Okay, consider the problem of 3 colorability, that is deciding if a given undirected graph is 3 colorable. Same thing. In a related problem called pad 3 colorability, one has to decide if a given graph is 3 colorable. But the input is a description of a graph followed by 3 to the size of v many hash symbols, where v is the number of vertices in the graph. Which of the following is the smallest class that contains pad 3 colorability? Okay, and now it is in terms of time. Okay, now it is in terms of time. Okay. So what they are saying is, okay, same thing, 3 colorability only. Okay, but slight modification. This time, three colorability consists of all the x followed by hash to the size of v. Okay, where x is a graph description of graph G, G or vertices, some V vertices, E edges, and which is three colorable. Okay, which is three colorable. Now, as you can see, the input is greatly inflated. Okay, the input is greatly inflated. Question is now with this inflated input, okay, and n denotes the input size. Okay, what is n? Here, n is the input size, which is size of the graph plus 2, not size of v. Okay, slight mistake. Look here, the 3 to the v many hash symbols. It's much more than v. Hash to the 3 to the size of v. So this is 3 to the v. Okay. This is the input size, which is n. Okay. Question is this pad 3 colorability. Okay. This pad 3 colorability. What is the time? Is this it takes? Is it easier? Is it any easier or any harder than the original 3 color? Okay. Yeah, go ahead.
Yes, so can you explain this pad 3 colorability problem, because this is not clear to me, except that this so x is the description of the graph, and what this pound stands for, what number of the symbols or what?
What?
So what this pound, I mean this symbol x dot.
Oh, okay. Okay, sorry. The hash is just a symbol. Like you can imagine the Turing machine to have symbols, tape alphabet, okay, that we call it gamma, right? To be 0, 1, hash and blank. So there is this extra symbol.
Okay. And why this 3 raised to the power b and raised to the, I mean this symbol raised to the power of 3, I mean what is the interpretation of this?
Oh, this means this is like something from automata theoretic kind of thing, where hash to the 5 means 5 times hash. This symbol is given 5 times. So a hash to the 3 to the size of v means so many hashes that there are 3 to the size of v many hashes following the actual input.
Okay.
So you get it, right? That's why I'm saying we are inflating the input. Padding does this. So this kind of argument, if you remember, is used in showing that if np equals p equals np, then exp equals next. We used padding to show this. Okay. So okay. In the lectures, yeah. So now we have this. So yeah, any idea?
So what is the question?
So the question is to solve this new padding 3 colorability. So you need to tell whether you need to ignore all the hash symbols, okay, and just tell whether this whatever graph x is representing, is that graph 3 colorable or not. Okay. Just 1 moment. I'll get some water. Think about it. Oh, sorry, the display is gone.
Yes. Can you show the screen again?
Yeah, sorry. Okay, Suraj. Order n. Okay. Oh, sorry. Yeah. D time n. That is right, Suraj. Okay.
The point here is that what is the benefit of including this hash symbol here? Because otherwise, if I do not include the hash symbol here, then this problem is NP complete.
Yeah, NP complete. Right.
Yeah. So what impact this hash symbol brings to us to reduce the complexity?
Mm-hmm.
Yes. So uh, n denotes the input size and n is equal to, okay, so the entire thing is equal to n. That is the size of the graph and then plus 3 raised to the power v. This entire thing is called
Right.
n.
Right.
Okay. So yes, and for every vertex, I have got 3 number of the possibilities. Okay. So when I select the first vertex, so then I will maintain 3 hash corresponding to one vertex in x, corresponding to one value in x. I would be maintaining say 3 pound values.
Okay.
And 3 pound values say so but this help, I have no clue, no idea.
Yeah.
So I have no idea.
Okay. Yeah, no problem. Yeah. Okay. So Suraj, you wrote order n, right? Can you tell what idea you have? Hello.
Sir,
My internet is really bad. I cannot. Yeah. Say it
if
again.
if the input was just 3 to the power b
Right.
because something right, but now the input is it is O of n in terms of input, just the graph. So by brute force of vertices, but now the input is inflated by the order of 3 to the power b vertices. So it is order of n in terms of input.
Right. Good. That's right. Yeah. So the idea here is as follows that see the idea is here as follows that see we've inflated the input by a lot. Okay. And this is already some order. This on representing G as an adjacency matrix. Okay. This is something like order V square. Okay. If you represent it as an adjacency matrix. Okay. Order V square.
Yes.
And if you look at the hashes, they are very large. It's 3 to the size of V. So the gap, so between the size of this and this is exponentially large. Or in other words, X is exponentially smaller than the rest of the input. Right, X is less exponentially large, smaller than the rest of the input. So the idea is that, and these are just redundant, right? We don't need them actually. We don't need them at all. So the idea is as follows that if I even if I do a brute force approach to solve 3 colorability on this part, it'll take me exponential time. But exponential time on this very small value. Since it is exponentially small on this, and then I apply brute force on this, even if it is exponentially large on this, it is not very large. That is the idea. Okay, that is the idea. I'll tell you the exact proof for it. Okay, so the proof is the same as before. This logic of going across all. Okay, so here's the algorithm. Okay, algorithm. The input is let me call it y equals x times 3 to the x times hash to the 3 to the v. This is my input, and now step 1 is, first thing I do is I go till the end hash. Okay, scan y from left to right and extract x from it. So I keep a pointer. I keep going right until I see a hash symbol. Then I'll say, okay, everything before that is x. Okay, so that is the first thing I do. Now I've got x. Okay, so suppose x represents the graph G on vertices V and edges E. Okay, now I use the brute force algorithm. Go across all red, green, blue to the power V. So it means strings of length V where each symbol is either red, green, blue. Okay, or in other words, go across all 0, 0, 0, 1, 1, 0 equal to the V strings. Go across all, I'll call it, let me call it sigma, gamma. Okay, and this represents red, this represents blue, this represents green. Now this is the assignment, and check if 3 coloring violated every time. And finally, if no, output yes, the output yes, if it is not valid. Otherwise, after the loop ends, output. Okay, so the same thing is happening. You go across all combinations, and remember what were the number of combinations? 3 to the v many possibilities, right? That time we had a possibility of reusing space, but now we are talking about time. So how much time will it take? 3 to the size of v. Okay, number of possibilities of gamma, which is the assignment. Okay, this is in 0, 1, 1, 0, 1, 1. There are 3 types of symbols, and there are 3 choices for each vertex, so it will take 3 to the size of v. So time taken, what is the time taken? Firstly, I take a counter which goes till the end. Okay, which time taken is size of the x, which is around v squared since it's given as adjacency matrix, plus 3 to the size of v. And this is to go across all the, this 3 to the v is to go across all the gamma possible assignments, and then this will take, this checking whether it is violated will take another go across all pair of edges, right? So this will take another n choose 2, which is some v square time plus size of v square time, which is still order of 3 to the size of v. Okay, until here it's fine, right? time taken is order 3 to the v. Is it clear? Well, okay, well, it's already given thumbs up. And what is the input? Input size is n, which is size of v square plus 3 to the v. So this is the input size and this is the time taken. So it means our algorithm results that paired 3 colorability is in d time n. Is this clear? Goel, is it clear?
Yes.
Okay. Yeah. So this is the concept of padding. Okay. Okay. Good. So we are done with assignment questions. Now we'll begin this week's content. Okay, which is based on randomization. So before I move on, I want to. Sorry, how do I delete this page? Okay, right. I need to add square paper. Right. Okay. Yeah. So before I begin that, okay. So we don't have much things to cover because randomized classes are just introduced recently. Okay. So I just want to give a brief introduction, okay, and do a brief recap. So we see our hope is to find deterministic algorithms always, okay, and our dream is to find efficient deterministic algorithms for every problem. So efficient in terms of time usually, and this is captured by P. Okay, and if you want to talk about space, then it is captured by L. Okay, and if we give it slightly more power, which is give non-determinism, okay, the power of guessing correctly, then we get NP. Now, so always efficient algorithms, deterministic algorithms may not be possible. So that is when we turn to something called randomized algorithms. So what is meant by randomized algorithms is that if I am in a current state, then the next step of the algorithm is not clear. Okay, it is not determined, it is not deterministic. Okay, so the next state is not not completely determined by current state. So there is a degree of randomness here. Okay, so the best way to actually capture it is that my algorithm actually tosses coins on the way. Okay, so I am in a current state, I want to make a decision, then I'll toss a coin. Okay, and the coin may be heads or tails. Okay, algorithm tosses coins during computation, and it may be heads or tails, which is 0, 1. Okay, and depending on whether it lands on a heads or it lands on a tails, I'll make my next move. Then the next step should be this. Then the next step should be that, and so on. Surprisingly, we know of problems which can be efficiently solved by randomized algorithms, but it is not known whether we can solve it using efficiently using deterministic algorithms. Okay. So now what we are interested in is, see it from a complexity theory viewpoint. Okay. So that's why we want to now define classes and so on. Okay. And in that light, let us talk about complexity classes. Okay. Which is the first complexity classes we would like to see is RP. Okay. Which is called randomized polynomial time. So these randomized algorithms take polynomial time, and this is the particular characteristic is that it is consisting of one-sided error. Okay. So what it does is, if a language L is in RP, if for all x in L, not for all x in 0, 1 to the n, okay, x is in L, then what happens? Then my and if L is if and there exists a probabilistic Turing machine, which means it will toss random coins on the way. Okay. If x is in L, then probability that m on x accepts, since it's randomized, there is a probability involved. It may not always give you the good answer. Okay. Oh yeah, by the way, before I should have told you that. But what is the problem with randomized is that it may not always give you the right answer. Okay. But it is applicable in scenarios where you are worried more about the efficiency rather than the quality of the answer. So it's a trade-off. Okay. So it's a trade-off between efficiency, time taken, and quality of the answer. So it may give you wrong answers, but obviously if it always gives you the wrong answer, it is not helpful at all. But if with a good guarantee it tells you the correct answers, then it is good enough for us in a lot of scenarios. And practically randomized algorithms are used left and right. For example, Google's indexing algorithm, Google search algorithm, and these Facebook's algorithms on very large graphs, all these social media apps, they all are randomized algorithms, because you cannot hope to run a deterministic algorithm on this, because it will take too much time. You'll have exponential amount of time on billions of nodes, which is not feasible at all. Okay, so the probability that x accepts is at least half. Okay, so you have this guarantee, and if x does not belong to L, then probability that m accepts is equal to 0. So there is no error if it does not belong. Okay, so this is about RP, and similarly you have coRP, which is the complement, and here if x is in L, then it's opposite. If it does not belong to L, then probability that m of x accepts, then we have no error if it does not belong. But if it belongs, then we have error. Is at least 1 by 2. Okay. Now RP, then we have BPP. BPP stands for bounded probabilistic polynomial, which means two-sided error. So you have, it belongs to BPP and so on and so forth, X is in L, then probability that M accepts is 2/3 at least, and X does not belong to the language, then probability that M accepts may also have an error, which is at most 1/3. Okay, 1 minus 2/3. Or you can even say this, you can even say the probability that it rejects is high. This is also a valid way to say. Okay, and final class we have is ZPP, which is quite interesting, and there are two definitions for it. I'll tell you one definition only for now. That is, ZPP means there exists a language. Sorry, what I'm saying. There exists an algorithm, or a probabilistic Turing machine. Same as a randomized algorithm, same thing. There is a probabilistic Turing machine running in expected polynomial time. Running in expected polynomial time without errors. What does this mean? The idea is in the name itself. ZPP stands for zero error probabilistic polynomial. So there is zero error probabilistic polynomial. It runs in expected polynomial time, which means, what does expected polynomial time means? Over the choice of random bits, the coin tosses sorry, over the choice of coin tosses, the machine runs in polynomial time on average. Is that clear? So what are the containments? Okay, I quickly want to recall. So you have the following. Okay, so first, okay, so you have P, and P is contained in RP, because as an RP algorithm, one-sided error. Remember, RP is error only on one side. So P qualifies as an RP algorithm because it accepts with a probability 1. And if it does not belong to the language, it will reject it with probability 1 or accept with a probability 0. So P is contained in RP. Clear, right? And is RP contained in BPP?
So in case of RP, yes. So RP is that if the string belongs to if the string is the part of all the strings which are the part of the language are getting accepted with the probability greater than half, and which are not the part of the language are getting accepted with the probability of 0. And in the BPP, these limits are 1/3, and then accepted with the probability of greater than 1/3, and okay. So, but then this 1/3 can be brought down to the level of the half, I think, and in both the sides. So therefore, RP in this case will be the subset of the BPP. Yes, it would be.
Right. Because RP is then probability that accepts is greater than half, and here if it does not belong, then probability that it accepts is equal to 0. And BPP, if it is an L, then probability that it accepts is greater than or equal to 2 by 3, and you are right that these constants don't matter. So half you can actually increase it to 2 by 3. Okay, there is this. I think you've seen it in the lectures. There's something called amplification, right? Success amplification, and these constants don't matter. You can change 2 by 3 to 1 by 2 or even 9 by 10 or something like that. Okay, and x is not in L, then probability that it accepts is less than or equal to 1 by 3, which is, and here it is 0. So any RP algorithm is a BPP algorithm. Because RP algorithm is just BPP algorithm with no error in the negative component, negative membership. So now, okay, PRP is done. You can argue the same argument will hold for coRP also.
Yes.
Right. Yeah. Yes. Now, can you tell about ZPP?
So for the ZPP would be, since things are pretty sure. So in RP, this is one side, in coRP, the other side. So if I take the intersection of the coRP and RP, so I would be having the answer of both. So I
Right.
think Z would be the intersection of coRP and RP.
Right. ZPP is contained in coRP intersection RP. In fact, you can improve this to ZPP is equal to coRP intersection RP. ZPP is equal to RP intersection coRP. Good. So now this. Okay, good. Now, can you tell me okay, good. Now, can you tell me what about P and ZPP? Can you say that P is contained in ZPP? Or can we not say that? P versus ZPP question.
So in case of the P, we are pretty sure about both yes and the no. And for the ZPP also we are sure. But then for the ZPP we do have, apart from this sureness, we have don't know condition also, kind of a thing.
What condition?
Don't know. Matlab, I have
Oh, don't know.
something I mean.
Yeah. But okay. Don't know condition is there. Think of this definition with what I've written. Okay, it's in a very bad handwriting. Okay. Running in expected polynomial time without errors. Yeah, the don't know is the second definition. This is another definition of ZPP. Both are equivalent. Okay.
Yes.
So there exists a probabilistic Turing machine running in expected polynomial time. Now, what is expected polynomial time? Over the choice of random bits, machine runs in polynomial time on average, which means the ZPP algorithm, remember the ZPP algorithm may take exponential time. It is not that it will always take polynomial. It may take exponential time, but let's say on one choice of random bits. Oh.
Your video
Yeah. One moment. My internet is. Is it fine now?
Yes.
Yeah. Sorry. Yeah. Where was I? Yeah. So your ZPP algorithm, on some choice of random bits, it may take longer time. It may take exponential time. On some, it may take shorter time. Okay. So ZPP algorithm on some choice of random bits. Okay, and it makes coin tosses on the way, right? So this is the computation graph. Some of them it may take very long time, and on some of them it may take just polynomial time. But if you take their average, okay, so this is time taken by the first path, time taken by the second choice, time taken by the third choice, and so on. If you take their average, t let's say total there are m many possibilities, and if you take their average by m, then this is polynomial. So in other words, you can even say that okay, the most of the random choices actually lead to polynomial time. This is another meaning of ZPP. On average, it takes less time.
Yes.
Okay, so you may already see the connection between don't know definition and this definition. It is only a matter of rejecting when it says don't know. Yeah. Anyway, um, so now with this new definition, can you compare ZPP and P? Suraj, are you able to hear?
Yes, sir.
Yeah. Okay. Yeah. So the question is, okay, with this new definition of ZPP, alternate definition of ZPP, can you compare ZPP and P?
So, I mean, since in ZPPP, the quite possible that the for some of the problem, right? So the time could be exponential also, and which is not possible for P. So therefore, I think that this P would then be the subset of the ZPP.
P is subset of ZPP, that is correct. Yeah, Suraj, P is contained in ZPP, that is correct. But the reason you gave is a bit strange. You said since ZPP, the coin toss, the coin toss is not possible in P. You said P is contained in Z. But okay. That is an argument to say that that is an argument to say that. One moment, okay. My pencil is what? Just one moment, guys. Right. Okay, sorry. I was worried for a second. Okay, so right, so that would be an argument to say that P is not contained in ZPP. This is an evidence for that. But the other way around, P is contained in ZPP. Yes, Suraj, what any? Why is P contained in ZPP?
So I said that since in the case of ZPP, expected time is linear, and expected is
Polynomial.
Expected is polynomial.
Right.
Expected is so yeah. So the thing is, since expected is polynomial, so we may have exponential, and we may have since we can have exponential thing, so therefore P is contained in ZP.
It's almost close. You are very close. Don't go towards the exponentials. I'll give you one hint. Is every P algorithm also a ZPP algorithm?
Yes, it is.
Exactly. Yeah, Suraj. Right. So take any P algorithm. It does not have any randomness, but just assume that okay, randomness is just one string. There are not a bunch of strings. Okay, there is only one computation path. So this is the random coin toss is just one string. Then it runs in polynomial time, which means over the choice of random bits also, it runs on average polynomial time only, since it already runs in polynomial time. So every P algorithm is also a ZPP algorithm. So you can improve this to say that P is contained in ZPP. Okay. Okay, good. So this is the current landscape that we have. And then NP, NL, and so on. You can fit and Yeah, NP is an interesting one. Okay, so I want you guys to compare NP and RP. Okay, requires a bit of thinking. Think about it.
So I think RP is contained in MP
Okay,
because
okay,
in case of MP, all the strings which are the part of the language are getting accepted with the probability greater than 0. And all the strings which are not the part of the language are getting accepted with the probability of 0. So strings which are not the part of the language, for them NP and RP both are same. And for the strings which are the part of the language, NP requires the probability greater than 0, and whereas the RP requires the probability greater than or equals to half. So therefore RP would be contained in that.
correct, correct, exactly, exactly. So for NP, the probability of accepting is greater than 0, whereas for RP, the probability that it accepts is greater than half, right, for the yes instance, and the other half is probability that it rejects is equal to 0, and probability that here also it is rejecting is equal to 1, you can say. Rejecting when, yeah, for no, for yes, for no it rejects is equal to 1, right? So any RP algorithm you take is also an NP algorithm, because if you want to make a non-deterministic Turing machine, just run the RP algorithm and it will make coin tosses on the way, that is fine, but by at least half probability it is already correct, and NP just tells you strictly greater than 0. So NP is actually, any RP algorithm is also an NP algorithm. So NP is contained in RP. Okay.
For other viewers, NP is not contained in
Oh,
RP.
sorry. Yeah, right. NP is contained in RP is contained in NP. Okay. Okay, good. Another way to see it is, okay, I have my Turing machine and it makes coin tosses on the way. This is the configuration graph, or you can say computation graph, whatever. And it makes coin tosses on the way. On 0 it lands here, on 1 it lands here. On 0 it lands here, on 1 it lands here. On 0 it lands here, on 1 it lands here. These are the coin tosses on the way. Now, what is and how many, and let's say it takes polynomial time, right? How many total possibilities are there at the leaves? It will either be an accepting path or rejecting path, right? How many possibilities are there? There are 2 to the poly n many. The number of leaves is the height of the 2 to the height of the tree, right, for a full complete binary tree. Now these many possibilities are there, these many paths are possible. What does NP say? NP says at least one of these paths should be accepting. Okay, at least one of these paths should be accepted. What does RP say? It says half. Okay. For NP, at least one. And for RP, half of these should be accepting. BPP is slightly more nuanced. It talks about accepting as well as rejecting. Okay, so now you have a question about correctness, but you can see, right, that when you talk about an RP algorithm, when it belongs to the language, then all of them, at least half of them, should be accepting paths. When it does not belong to the language, all of these nodes should be rejected. And so on. This is an alternate way to view it, which is quite helpful in certain situations. But anyway, we have RP is contained in NP. And which brings us to the first question that I want to discuss. I'll copy this. It is question 2. Show that ZPP is contained in NP. I think, can I take a screenshot and then 1 moment. Take a screenshot. And paste it here. Question 2. Show that ZPP is contained in NP. Interesting. Wait. Okay. So this is the diagram. We now also know that OONP contains ZPP.
Yes, so ZPP is contained in NP because for ZPP we have for all the strings which are, ZPP is always correct. So for ZPP we have yes, so expected time is polynomial, and sometimes exponential, sometimes polynomial, and that's the case with NP as well. So
No. NP, if in all paths it takes polynomial to NP, is it not?
yes, NP takes polynomial.
So the same block, yeah.
So I'll go for the second rule then. For ZPP, we have answers as either yes or no, or the don't know.
Okay.
And the NP, we have answers as yes and then for no. So in case of the ZPP, every time ZPP is correct, and at every time NP is also correct. NP cannot be wrong. So all the strings which are the part of the language are getting accepted with the probability greater than 0, and which are not the part of the language are getting accepted with the probability of 0 in case of NP. So are getting rejected with the probability of 1 in NP. Therefore, ZPP includes, NP is slightly wider in the sense that the probability should be greater than 0 for all the strings which are the part of the language. However, for the ZPP, we do have either the probability greater than 0 or we have another option of saying don't know. So
yeah, that is right. Don't know is actually causing a bit of a problem here. What do you do?
So I mean to say that we won't be saying don't know more than half of the times. So we would be saying don't know less than half.
Right. So right. So let's use your definition. Okay, it says yes, no, or don't know, and don't know it will use less than half of the time. Now your let's say X belongs to the language, and you run it. Okay, and on all these outputs, and it either says correctly yes. So if it belongs to the language, on all paths that it does not say, it will say yes, and for some of the paths it will say don't know, and it will say at most half the time. So in the case that X belongs to L, this is fine. Yeah. So what do you do in case it says don't know? Just reject it. Now let's say X does not belong to the language. Let's try it. And this is your machine, and it is running, and if it says yes or no and on a certain path and it does not belong to the language, it will definitely say no. That is, it is a zero error, so it will never say yes, and it will say don't know half of the time, but we are setting all don't know to reject. So yes, it qualifies as an NP algorithm. Right. So the algorithm is as follows: run ZPP machine M, and on X, if this is the NP algorithm, if yes, then accept, if no, then reject, if it says don't know, then reject. Yeah, this is an NP algorithm. This is valid. Yeah. Suraj, is this fine?
Yes.
Yeah. I actually, so can you come up? Okay, so that's good. I think I had seen this proof somewhere, but I did not have this in the mind initially. So is there an alternate way to show that ZPP is contained in NP? But good, this is yeah, this is one way to show. This is a direct way to show. Firstly, so an alternate proof. Use the fact that RP is contained in NP, and okay, and question to you is ZPP contained in RP? Is this true?
So the question is that okay, RP is subset of the NP,
Right.
and now whether ZPP is there in RP.
Because if
Okay.
this was true, then directly you can put ZPP inside NP. Yeah, go ahead.
Yes, so but ZPP is equals to the intersection of RP and then coRP.
Good.
So if it equals to the intersection of RP and then coRP, then it shows that some of the portion of the ZPP would belong to the coRP as well, and not only to the RP.
Yeah.
So,
but
so
be careful. This is talking about intersection, so we can say something more.
yes. So I mean something
Not
which is
union.
so yes. So yeah. So yes. So intersection. Yes. So definitely it would be there in RP. Yeah. So
Exactly.
yeah. Intersection. Yes.
Yes, exactly. The fact that it is intersection means it's contained in RP also, it is contained in coRP also. Right. So, which definitely implies that ZPP is contained in RP. Good. So, what does this mean? This means that ZPP, and let me call it 1, is contained in NP from 1 and 2. Let me call it 2. This is an alternate proof for it. Okay, and that this algorithm was another proof for it. Okay, so
Sir,
yeah, Suraj.
can you summarize the first proof in short? That
Okay, I'll do that.
Don't know, then we reject.
I'll do that. Okay, quickly I'll do that. So another way of saying ZPP is there is an algorithm that gives that answers correctly without error. Okay, correctly either yes. Okay, and this algorithm is randomized. Okay, it either says yes or no or don't know. Okay, it could say any three of these things, and of course it may be that the algorithm will always say don't know, right, and which would be very bad for us. But the good thing is that the number of times it says no is don't know is low. Okay, the probability that this algorithm says don't know on any input is less than half. Rest of the times it will say yes or no, and it will say without any error. Okay, so what does the computation graph of ZPP algorithm look like is that it tosses coins on the way. Okay, and then it has these exponential number of leaves. Okay, so this is the and by the way, it takes polynomial time. There exists a randomized poly time. Okay, and this takes polynomial time, and it tosses coins on the way. It says 0 or 1, tosses coins on the way. Okay, and after so many coin tosses, less than half of them will be don't knows. Okay, and what happens to the remaining? The remaining could be accept or reject, right? But since it's a ZPP algorithm, it always answers you correctly. If X is in the language, then all of these are accepting. And if X is not in the language, then all the randomized paths will correctly tell you to reject. This is the computation tree way of looking at it. Okay, so if it is in the language, then it will correctly tell you that, oh, okay, keep X. I mean, all of the randomized paths will actually tell you to accept. The rest will tell you don't know. And if it is not in the language, then all of them will tell reject. Okay, now how do I convert this algorithm to an NP algorithm? I want to show that ZPP belongs to NP. ZPP is contained in NP. Idea is, okay, simply if ZPP algo says don't know, then reject. This is the simple idea. Okay, so here is the algorithm. Just simply run the ZPP machine on X. If it says yes, accept. If it says no, then obviously reject. If it says don't know, this is the problem, it'll say reject. Now why does this, why is this qualifying it as an NP algorithm? Okay, so you have, say, X is in the language, then you have your computation tree, and X is in the language means all of these accept, and half of these, less than half of these, actually said don't know. These are all don't know. But what I'm saying, our algorithm is rejecting here, right? When X is in the language, what does NP say? NP says if X is in the language, at least one path should be accepting. So there exists at least one accepting path. How is that guaranteed? Because the number of don't knows is small, it's less than half. So the rest of them must all be accepting paths. So this means that there is at least one accepting path, right? So as if the condition is satisfied for NP, for accepting, accepting. What if it is not in the language? Now again, it makes coin tosses on the way, and it is a zero error machine. So if X is not in the language, it will always reject correctly on all coin tosses. and the rest it'll say don't know. Right. But what is our algorithm saying? If it says don't know, then our simulation will reject. So if it said don't know, then it will reject. In other words, if X is not in the language, all of our coin tosses are rejecting. And what does NP say? NP says if X does not belong to the language, then for all computation paths, or in our case, for all coin tosses, machine rejects. Which is the definition for NP machine. That if it does not belong to the language, then there is no accepting path. So Suraj, is this clear? So now,
Yes, sir, clear.
yeah, okay. So yeah, so now we've converted our ZPP algorithm into an NP algorithm, and how much time will it take? It will take polynomial time, because our ZPP, this definition of ZPP algorithm runs in polynomial time. Okay, CoL also it's fine. Okay, good. Okay, so how much time do I have? Okay, I have half an hour. Good. So we'll do other questions. Good. So we'll finish the ZPP part. Okay. So okay. So yeah. So can you look at these questions? A, B, C, D. Which of these options are correct?
So yeah, part A is correct because just now we have discussed yes, no, and then don't know thing. And secondly, language accepted by the PTM correctly says yes or no and false with expected polynomial time, which you said. So therefore, this is also true. And ZPP Las Vegas. So I don't remember that which algorithm always gives the right value. Either it is Las Vegas or the Monte Carlo. I think it is Las Vegas, which
Okay.
always gives the correct answer.
Right.
And yeah, and but then it may take long time, but will always give the correct answer. So
Right.
ABC are options are correct.
Okay. Okay. Suraj.
Uh, for me, only A and B. C, Las Vegas, I don't know.
Okay. Okay. Yeah, only A and B. Okay for you. Okay. Yeah, well, you are correct actually. So yeah. Also, Suraj, for your information, ZPP exactly captures what are called Las Vegas algorithm in the algorithm design scenario. Okay. And A and B we already know. Okay. C. So Las Vegas algorithms are those algorithms. Now in terms of algorithms definition is that they are always correct. Okay. Um, always correct and run in theta polynomial time. Okay, or in other words, on average polynomial time. So these Las Vegas algorithms are exactly ZPP algorithms. Monte Carlo algorithms. Yeah, I'm not sure about that. I am not sure whether it is exactly BPP or RP. Okay, I'll do a quick search. Let's see. Monte Carlo algorithm. Randomized output may be incorrect with a certain typical small probabilities. Monte Carlo, so it is RP, I think. BPP. So Monte Carlo algorithms So these are named after cities where casinos are famous for its casinos. So to do with probability. So Monte Carlo algorithms, okay, are having errors, but run always in polynomial time. Okay, so and this is exactly BPP. So a lot of times they are also called Las Vegas algorithms and Monte Carlo algorithms instead of saying ZPP algorithms or BPP algorithms. So Las Vegas algorithms is the correct answer. I don't know what is wrong with my pencil. Okay. Okay, so those were the answers. We are done with that. How much time do I have? Okay, now which question do I want to do? That's the thing. Okay, let me try one. Okay, I think one we can complete it within the time. So I'll paste this here question. Okay. Okay, I'll come back in 2 minutes. Please stare at the question. I'll remove the screen timer, or this will turn off. Not screen time. I think it will be in battery. Screen off. What is it called? Screen. No, I think since I turned off the low power mode, it will be fine. Our display and brightness. Auto lock is. I'll keep it to 15 minutes. Okay. Yeah. So stare at this question. Generalize the definition to log space instead of polynomial time, and think about it, how you can simulate in polynomial time. Okay, I'll be coming in 2 minutes. I'll give you one hint. Okay, the hint is to use matrix multiplication. Okay. Yeah, hi. So, any idea?
Yes, so since L is contained in P,
Okay.
so since L is there in P, so uh, therefore this BPL class would also belong to P, because for the BPP, because it's a bounded error case. So for the P, we are pretty sure about yes and no, and for the BPL, we are not that much sure.
Hmm.
So L are bounded. But then, as far as the space requirement is concerned, so since L is a subset of the P, so therefore, yeah, so therefore this is true.
L is a subset of P. Therefore, BPL is contained. Why should this follow? It's not very clear to me.
Okay, so it would follow because for P, the probability that all the strings are which are the part of the language are getting accepted with the probability of 1, and
Hmm.
not the part of the language are getting accepted with the probability of 0. And in the case of the BPL, the strings which are the part of the language are getting accepted with the probability of say greater than half, and not the part of the language say is less than half kind of a thing. So both the intervals of the this BPL are contained in the interval for T. And as far as the space requirement is concerned, so since it is a PTM occupying the log space. So log space, is there inside the P.
Yeah,
So
but
input.
see, the idea you gave actually shows that BPL is contained in BPP, because what you're telling is simply simulate the BPL algorithm, and the BPL algorithm, what will it do is uh, it may give me wrong answers, but it'll have some errors. No, if I simply run the BPL algorithm using my P machine, yeah, I'm convinced that it'll take polynomial time, but it'll have some errors. No, because it's a BPL machine. So okay, I'll BPL L is in BPL. Okay, if there exists a probabilistic Turing machine M, okay, uh, using log space, and such that for all x in 0 1, x is in the language, then probability that mx accepts is greater than 2/3, and x not in the language, then probability that m accepts is less than 1/3. Okay, so this is the same definition, only changes the log space. And now what you're saying is this BPL algorithm will also be a P algorithm. That's what you're saying, no? Well,
Uh, yes, but then I'm wrong at this point because yeah,
right.
because there is for the strings which are not the part of the language, for them the yes, no, I'm
Exactly.
wrong.
Even for strings that are in the language, I have some errors. Although fewer
Yes,
errors, but there are errors, right? And if you simply run it using P machine, first question is what do you do about the randomization? Because BPL is a randomized machine. How do you feed the random bits? Because my machine I want to make should be deterministic.
yes.
So
So
as
the
though
point here is that since this probabilistic Turing machine is occupying the log space only, so something is hidden in the use of this log space thing actually.
right, log space is somehow important.
Yes, and because of this log space thing, there won't be any chance of error. So I'll have to verify this that how to restrict the use of the log space will make the possibility of committing errors is equal to 0.
Right.
So so but log space, if something is occupying the log space only, then the time at the most it can take is polynomial. Uh, so if the time is polynomial thing, linear rather, so then
Close, somewhat close.
yeah, not so sure.
Yeah, but close. The fact that it is running in log space, the the configuration graph is actually, the number of configurations is actually small. Right. Oh, I need to charge my laptop. Okay. So, okay, I will. I think the full answer will take a long time. Okay, but I'll give you a simple. Okay, next time we'll discuss it in detail. But I'll give you one idea. Okay. So let us see. Yeah. So first thing is that what does the configuration graph of the machine look like? Okay. So our machine makes a few coin tosses. Okay. Now here's an important concept. Okay. About random bits being fed externally. What you can think of is that our machine, which is randomized, makes some coin tosses on the way. Another way to view it is, instead of making coin tosses on the way, I give it the coin tosses. I give purely random bits externally. And whenever it needs to toss a coin, it will look at that particular random bit. Okay, at the particular position. That is another way to see it, and this is equivalent, I hope you can see. And any configuration. So what does a configuration of Turing machine have? Should have the state, head position, right, and tape content, and the coin toss. And but the coin toss is not exactly a part of the configuration, so we'll just leave it here. Okay, so this is the possible configuration. And remember, this was the argument to show that L is contained in P. So the state is Q. Okay, so this, how many states can there be? Constant. How many head positions can there be? Logarithmic. So how many bits are needed, and how many bits are needed to show the tape content, which is again order log n. So how many different configuration, number of configurations, is equal to 2 to the order log n, and which is polynomial. And this is the number of configurations, so I can make a graph out of it, where each of these nodes are configurations, different configuration. And what is the size of the graph? Is G. And now is the important part. Now I say that, okay, if I am at a particular configuration and I toss a coin, it's either 0 or 1 on that same input X, then I lead to two different types of configurations. Then again, if I do a 0 or 1, then it will lead to two different types of configurations, and so on. And this is one observation. And separately, but it's okay if you don't understand right now. Okay, next time I'll discuss it in detail. Separately, you have the adjacency matrix. Okay, adjacency matrix. Oh, okay. A few concepts are required. forget about the configuration graph. I'll just do a simple concept, okay? Which is that, let's say I have a graph like this, and let's call it A. Okay. Let's say A, B, C, D, and A can go from A to B, and B can reach C, C can reach D. Okay, and what does the adjacency matrix look like? The adjacency matrix looks as follows. A can reach B in B, and B can reach C, D, and the rest are zeros. This is the adjacency matrix, right? Now, what is another way of, okay, what does adjacency matrix represent? Whether one vertex is adjacent to another or not. Now, another way of viewing adjacency matrix is that from can okay, A at a position uv means can I reach V from U in one step? Think of it as walking through the graph. Okay, traversing one edge is one step. Now think of A square. Think of A square. A square is A times A. So bring that 0, 1, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, and multiply it with itself. 0, 1, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0. Multiply it with itself. What do you get? Well, do simple matrix multiplication, you will get all zeros. Okay, so the first entry is 0. Second entry is this and this, right? So that is also 0. Third entry is this row and this row. This O, now you get a 1. And the final entry is this, and again you get a 1. And you keep doing this. And then you get a 0, that is this and this. And the other also you get a 0, the other you get a 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. This is what you get. And again, let's label them as ABCD. Okay. And now what do you get? Now let's make it into a graph. And A goes to C, A goes to C, and A goes to D. This is the new graph. So we've changed the graph now. It looks completely different. But can you intuitively, do you know what this represents?
Yes, so it represents
Exactly.
that in A and D there is one vertex in between.
Between A and?
So does there exist a path in between A and B with one vertex in between?
Yeah, but that is a very strange way to state it. Another way would be, can I reach V from, can I reach A to D in
2 steps?
In 2 steps, right? Yeah, Suraj also. In 2 steps. Good. Can I reach from in 2 steps? So, I can continue this then. This is an interesting. So, A to the N would mean, can I reach, okay, if I look at an entry UV, can I reach from U to V in N steps? Try to formally prove it, okay? It's very simple to prove it, but it's a very interesting exercise. That powers of the adjacency matrix give us a way to test reachability. Okay, so now I can, so this is something like reach n. Okay, reach n is GST Okay. Can I reach or not? Can I reach? Wait. There exists path of length n. Okay. There exists a path of length n from S to T in G. Exactly n. So this is reachable. Yeah, good. So uh, so you can see, right, on finding these powers. So this is how powerful matrix multiplication is. You can actually do reachability. You cannot do general reachability. You cannot say if S, there is a path from S to T, but you can say that is there a path from S to T in n steps and additional parameter n. Okay, or let me change this n to k to avoid confusion. Okay, now now but the problem is it needs to be exactly n. Now let us come back to this configuration graph. Now I'm saying I can perform coin tosses on the way. Okay, I can perform coin tosses on the way on this polynomial sized graph, and we can make the polynomial sized graph because we are given polynomial amount of time, because we want to make a P algorithm finally, show that BPL is in P. It makes these coin tosses and goes into different configurations. Right. Now think of the adjacency matrix of the configuration graphs. So there are configurations here and configurations here. Now, if I go from a configuration A to a configuration B or C, depending on whether it lands on heads or tails, the probability that I go from A to B or from A to C are both half, right? So A on B going from A to B has half probability and half probability here. And the rest I'll fill zeros. Okay, this looks like multiplication. Wait. So on B, I put half. On C, I put half. And then I put zeros on the others. And zeros on the others. And here there are zeros. So this is a probabilistic matrix, or what is also called a stochastic matrix, where the sum of the rows is 1, columns of the row is also 1. This actually represents a probability. And similarly, I can make for the others also. For example, let me call it E and call this F and call it G. Then E on F and on G both give half. I mean, the probability is half on moving to F or moving to G. So I can make this configuration graph. Okay, so that is the second part of the puzzle. Okay, now the final part of the puzzle, I'll give it to you. So I'll copy this. Okay, now I have this. Okay, this is the probability matrix. Now what I do is I'll multiply it. So you saw right about the reachability. It will connect to reachability. Let me multiply it twice. Again. Okay. Let me paste it. So I do this. Okay. Now let's say my configuration graph look like this. Okay, from A it went to BC with like this on coin tosses, and on B and C, on B let's say it goes to E or some other arbitrary H, Okay, I think, and including H is E and H is just complicating stuff. So I'll not E and H, B, C, D, E. I'll just call it not D, D, F. Oh, no, no, D, H. Okay. So E, F, G is not there. So what do I have now is that on B, on D, and H, I'll get half, half. Again on B, on D, and on H, I get half, half. So what happens when I multiply it? Think about the reachability thing, what we did before. On A, I have B, C, okay, D, H. What do I get in D? And what do I get in H? What happens to the entries in D and H? Probability of reaching in 2 steps, right? Good, good. Probability of reaching in 2 steps. And what are the exact values? Exact values. And what will happen is this is again yeah, go ahead.
Yes, so because I lost the this connection in between, so I could not actually. I could only hear till that point that so we were computing the 2 steps, so that A square thing.
Oh,
So
okay. Oh no, so all this while it was not, when we talked about probabilities, it was not clear.
yes, so is this possible that you because this is pretty interesting? Is this possible that you cover this portion in the next session?
Yeah, definitely.
Yes, because we have another session from 8. I mean, so I
Oh,
was
okay. Sure. We'll do that then. We'll cover the rest. Okay. Um, and try to finish at least. Suraj, you heard the entire thing, I think, right? So, and you can try to complete this part of the puzzle. We'll start with this in the next week. Is that clear?
yes, sure.
In
Thank you so much.
Yes.
Yeah. Okay, we'll do that then. It's already 8 o'clock. Okay, so I think, yeah, you have other things to attend to also. So we'll break with that then. Okay, we'll start with this next time.
Thank you so much. Good night.
Okay, thank you. Good night. Okay, good night. Good night, Suraj.